Hello, everyone, and welcome to today's Keynote webinar titled The Path to Universal Newborn Sequencing. This webinar is a part of the Precision Medicine Virtual Event Series. I am Sydney Panilla of LabRoots, and I will be your moderator for today's event. Today's educational web seminar is presented by LabRoots. Before we begin, I would like to remind everyone that this event is interactive. We encourage you to participate by communicating with other attendees using our live chat feature during the presentation. You can find the live chat located at the bottom left of your screen. You can also participate by submitting as many questions as you would like during the presentation. To do so, simply type them into the Ask a Question box and click Submit. We'll answer as many questions as we have time for at the end of the presentation. If you happen to have any trouble seeing or hearing the presentation, click on the Help Desk button from the lobby within the event. Now let's get started. I now present today's speaker, Robert C. Green, MD, MPH, Professor of Medicine, Genetics, Mass General Brigham, and Harvard Medical School. For a complete biography on our speaker, please find it to the left of your screen. Dr. Green, you may now begin your presentation.
Thank you, Sydney, and hi, everybody. I previously had the privilege of speaking in this forum before, and I gave a talk in which I really tried to summarize my journey toward population genomics. I talked about returning a single gene, ApoE, which I got started on this with. I talked about being one of the first to return results within a research study, culminating with return of results in our own Mass General Brigham Biobank and return of sequenced results in the famous Framingham Heart Study and the Jackson Heart Study. Several thousand people in each who'd been whole genome sequenced but had never had any of their things returned. I talked a little bit about how in 2013 I got to lead a working group from the American College of Medical Genetics and Genomics, which came up with a list, which we called the ACMG list, at that time of 56 genes, which we concluded should be looked for and returned whenever anybody did a sequence for cause. So if somebody was getting sequenced for a heart problem, BRCA1, BRCA2, and a bunch of other genes were on this list, which we recommended. It had no force, but we recommended that every genomics laboratory look for and present, or at least offer back to people who are getting sequenced. We actually originally, for those of you who followed that, the interesting arc of that recommendation, we actually suggested that it be non-negotiable, not even requested, that just like you wouldn't put up an X-ray and report on the heart without reporting on a shadow on the lung, that every laboratory should do this in a required way. The ACMG board, interestingly enough, rejected that. There was a lot of debate about whether it should be opt-in or opt-out, and it was eventually made opt-out. And that served pretty well, because for labs that use it, someone now has to say actively, I don't want to see those incidental or secondary findings. And if they don't opt out, they get it. That's probably the most significant thing I've ever been a part of, in the sense that we created a new policy which offered people a chance to get secondary findings that they would not have already gotten. Now, even though it wasn't designed that way, the ACMG list became a little bit of a template for population screening. Even though it was designed around principles of incidental or secondary findings, it became a template, a convenient list that people could use. So along with other lists, like the so-called 10-gene CDC Tier 1 list and the Invitae 167-gene list, the ACMG 56, version 1, 56-gene list became a kind of template that people could reach for. In subsequent versions, it's been adjusted and added to, and it's gone up to version 3 or even version 3.2, which now has about 81 genes, and still serves in many IRBs and in many frameworks as a kind of endorsed list of actionable findings that can be given back if you're choosing to give something back. And then in my previous talk, I spoke a lot about population screening. I spoke about adult population screening, which we had pioneered with the MedSeq Project and NIH proposal that in which we comprehensively sequenced healthy adults, and we returned whatever we found to their primary care doctors without a genetic counselor in between. We trained the primary care doctors to sort of process these reports. Only took a couple of hours of training, and they got quite good at it. And then I touched in my last talk about the BabySeq Project, which was our pioneering project started 10 years ago, first in the world to sequence apparently healthy babies. And as many of you know, has now been joined by about 27 or 28 different projects worldwide, some in the US, some around the world, that are moving ahead with various models of sequencing newborns or early childhood. So today I'm going to repeat some of that, but at a deeper depth. I'm going to really zero in on the BabySeq project, spend a little bit more time on that. I will be repeating some of those slides and points for those of you who were here at the previous talk, but I'll also be showing some new data and some new slides and going into greater depth. I'd also like to try to finish, because this was a really robust and dynamic group. You had a lot of great questions last time. We ran out of time. I'd love it if we make this more of a conversation. So I'll try to finish at about, after about 30 more minutes, at about 38 after the hour or so, to leave plenty of time for us to hear your points, your conversation, ask your questions, and engage in the kind of really interesting back and forth that this topic deserves. So at this point, I will share my slides. I think you're going to then stop seeing me and just see the slide. So that should be it. Let me know, Sydney, is that working okay?
It doesn't look like we have visibility of your slides just yet. Let's go ahead and stop the screen sharing and start that again. Let's try one more time.
Okay, sure. Share my screen, window, PowerPoint, share.
Perfect. There we go.
Okay, great. All right. So now we're going to zero in on this path to newborn sequencing. And just again, as I always do, my support and disclosures are there, including co-founding two companies, Genome Medical and Nurture Genomics. If you or someone you know has a child that you want to get sequenced for screening, you can go to the nurturegenomics.com website and you can sign up on a wait list. The service hasn't launched yet, but we'll be launching later this year. So as one always does, this is obviously not me. This is a massive team of people who have worked over 10 years on the BabySeq project from all sorts of angles. Just make sure that we acknowledge that, but also the focus of this is on the costs, the benefits, and the risks of population screening, specifically population screening of newborns or young children. And so, as I mentioned last time, we've gotten to this point through about 20 years of research on incidental secondary findings, return of genomic research findings, and elective population screening. And the big take-home message from all of that is if you look hard enough, there's a lot there in the genome. Not everything, but there's 15 to 20% of healthy adults, and we're tracking 13% of children. When you look at 5,000 to 6,000 genes, actually are carrying a monogenic disease risk. As we'll come back to, that doesn't mean they're all going to get the condition. It means that you've identified a pathogenic or likely pathogenic mutation in them, and they are at risk for the condition. Of course, almost everybody's carrying a recessive mutation. Most people are carrying a marker that suggests an atypical response to one family of medications, whether or not they'll ever see that medication. And depending upon how many polygenic risk scores you search for, almost everybody could be carrying a polygenic risk score. If you're looking for 5 or 6 we end up seeing this in about 50% of people. And we talked already a little bit about how this correlates with the number of genes you're looking for. So if you're imagining a world in which a population of adults or children are screened, you have to ask yourself, how many genes am I looking for? And as most of you know, even whole genome sequencing may sequence all the genes. But remember, there's 20,000 genes. There's probably 10,000 genes that in some way, shape, or form have been associated with rare diseases. There's about 8,000 of them that are more clearly associated with those diseases. And most labs don't have a capacity to look for more than about 6,000. So when we say we're doing whole genome sequencing, what we're leaving unsaid is that, and we're selecting a set number of genes to put in the top of our funnel and that we're going to screen for. So moving on, as we said, to the BabySeq project, the reason that this becomes more urgent now is that there is a rigorous and vibrant pipeline of cell and gene therapies that is cranking, that has probably more than $1 trillion of investment from biopharma. And it is cranking out clinical trials and new treatments almost every day. It's actually been estimated that over 90% of genetic conditions could eventually be treatable with CRISPR, prime editing, and other types of gene and cell therapies. So obviously, you want to catch those early. You don't want to wait for those children to present after they've been damaged, particularly neurologic damage. So being able to identify hundreds of treatable conditions right now. This is a blind spot in pediatric care. They're not identified by systematic screening through the current newborn screening system. They're not identified in the pediatrician's office until the child presents and often goes through a long and tedious diagnostic odyssey. They are simply being missed and misclassified, misunderstood, misdiagnosed, and sometimes mistreated. So just as a reminder, we began BabySeq in 2013, and we sequenced the first infant in 2015. And when we did this for the first time, we found that there were 11% of these infants that had an unanticipated monogenic finding, something that nobody was expecting. Now, in retrospect, when you looked at the child for several of these, you did find subclinical or imaging or biochemical abnormalities, suggesting that yes, this condition was there, but not in a form that would have been recognized. This is important because it means you're not just talking about risk stratification. You're talking about two things. For a small subset of conditions, you're talking about a clue that allows you to uncover an ongoing subclinical but present pathological condition. For the majority of these, you're uncovering a risk stratification for a condition that has in no way that we can detect presented. We'll come back to this because it's really key to the debate on what's the value of this. The parents were not distressed. Now, keep in mind that these parents were self-selected, right? But our randomized clinical trial format allowed us to rigorously look with validated scales of parental depression, anxiety, and child-parent bonding in these three columns you can see here, the controls that didn't get sequencing at all, the dark blue in which people got, they got sequenced, but they didn't necessarily get anything concerning back, and the subset of babies that got a monogenic disease risk, where you would have expected the most distress, is the gray bars. But everywhere you look, these levels were equivalent, nor were there any sort of outliers that had catastrophic distress. So, you know, the sample size is not huge. This was a couple hundred families, not tens of thousands. And we know that there was certainly some mild upset when people found stuff, but they adjusted quickly. And we think the difference is that they were really understood what they were getting into. It's not that people can't be upset by bad news. These people really made a considered decision about whether to enter the study or not. And once they'd done so, they were psychically prepared for the possibility of quote, bad news, unquote. We also looked at downstream spending. And although, again, sample size small, yes, when you sequence people and not counting the cost of the sequencing, you actually spend a little more downstream. And if you want to break that down into what you're spending it on, you can see that you're spending it on additional blood tests, additional imaging, and additional subspecialty visits, either to a geneticist, a cardiologist, a nephrologist, or a dermatologist. So, but it's not as big as you would think, because there's a lot of noise in the system. When you've got a child from 0 to 1, they get all sorts of things. And there's so much noise in the system that there's not a huge difference in the spending that you account for with the kids with monogenic disease risk. Now, if this goes on over years and years, if there was a cardiomyopathy gene and you decide you've got to do an echocardiogram every year or every 2 years, that's going to add up. But in the very earliest stages, say the first 10 months after disclosure, not a huge difference, which is interesting. And then I may have blown through this quickly before, but I'll dive a little deeper here into actionability. So if you just ask yourself as a sort of thought experiment, what do I mean by actionability? It's a really interesting question. And I've done this with a lot of people, and they mean different things. For some people, this means, I think there's a pill I can give, or a tumor I can cut out. For some people, it means catching a condition early, even if you're not going to make a huge difference in the eventual outcome. For other people, it only means catching a condition early if you can make a meaningful difference. For some people, surveillance is just fine. For some people, even on a very untreatable condition like a severe developmental delay, some form of autism, they want to know because they want to be prepared, and because there's evidence that enriching the child's environment, the earlier you do that, the better the eventual outcomes. But it's very clear that not everybody means the same thing by this, and that we in genetics tend to take a much more concrete idea of this for very interesting sort of medical sociology reasons. We don't tend to endorse a lot of genetic interrogation unless we think that it's treatable. And it turns out that the lay public, on the whole, has a much broader sense of what's actionable. But I didn't rely on the lay public's sense. I took a semi-quantitative scale from ClenGen, to which you assign a 0, 1, 2, or 3 to each of these domains. The disease itself, how penetrant it is, meaning what's the probability that if you carry the mutation, you're going to get the disease. The disease severity, is it just annoying or is it really deadly? The intervention efficacy, how well does your intervention work? Is it really going to make a difference? That could still be surveillance, but is surveillance really important? And the intervention tolerability. An echocardiogram is much more tolerable than a voluntary mastectomy or oophorectomy. So the perfect actionability would be a perfect diamond. And we used Marfan syndrome as an example. It's pretty severe, especially if you count the aortic rupture that people can have. It's highly penetrant. It's got a highly effective intervention. You can save somebody's life just by following that aortic expansion and operating in time. And highly tolerable intervention. The surgery itself might be tough, but the echocardiogram that is needed for the intervention of surveillance is pretty easy. Whereas in Huntington's syndrome, down here on the bottom, severe condition, high penetrance, but no real effective intervention. And of course, if there's no intervention, it's not tolerable. So look for a perfect diamond shape if we think it's really actionable, and then look for some other shape less than a perfect diamond, or even this triangle upper right hand if we think it's not at all actionable. And here's what we saw, and here are the shapes we saw in the first cohort of BabySeq patients. there are very few perfect diamonds. The biotinidase deficiency comes about as close as you can get. But for the rest of them, there are components that go both up and down and to the left. So all of these, when scored, met the ClinGen criteria for actionability. Now, you get into an almost Talmudic debate with health services researchers and epidemiologists and about the degree to which there's cost effectiveness, over medicalization, um, because it's the same debate as a whole body MRI. Yes, you're going to detect some things early which are treatable, but how many other benign things are you going to detect that force you to act? And in that action could not only spend more money, but could actually hurt the person, taking them through biopsies to things that never needed to be biopsied. So that's the over screening and over medicalization debate that you get into. And you get into it in whole body, you get into it in a special way with whole body imaging and with the genome, because there's so many different things you can find. And each of them is going to have a different register of actionability. So it gets quite complex. Some of the scholars in this area will go down a road of modeling a single condition. We published a paper, for example, that looked at 9 childhood cancer predispositions in children, and it was close to cost effective. And that same group is working on, what if you just talk about cardiomyopathy? What if you just talk about sudden cardiac death? So that's really interesting. And the truth is, it's very hard to make those calculations because we don't know the penetrance of each of these mutations in the general population of children. There literally is there's no biobank, there's no collection, there's no way of saying, if I get this mutation, I know that 27% of the children are going to develop this condition by age 5 or something like that. We just don't know. We've got guesses, but we don't know. Now, and the concept of penetrance, again, the probability that if you have this mutation, you're going to have the disease, not get the disease, but have the disease, is really rooted in what happens in the geneticist office at one moment in time. Because what there we're looking at is usually a family structure where we found somebody with the disease, we find somebody else in the family with the mutation, and we say, okay, at this moment in time, whatever might happen in the future, this child or this adult does or does not have clinical evidence of the condition. And so almost every time you hear a geneticist talking about penetrance, they're talking about it in a slice of time, not in the context of an extended period of time, months or years or decades. Anyway, in the slice of time within the BabySeq project, if you look at the first 18 babies carrying mostly dominant conditions, we found 3 of those babies, just 3, who had features of the condition that we could discover, biochemical, imaging, whatever. And that results as sort of 17.6%. So that's pretty low overall. But then when we looked at the parent from whom they inherited that, and we actually said, A, do you carry the mutation? We found the parent who did. And B, do you have something that might be causally related to the mutation? We found several who did, in fact, have conditions that were causally related. And so a few more, in fact. So 23% of the parents had the mutation and phenotypic evidence of the condition. Okay, it's a little higher. Now, if you think about penetrance, which we almost never do, in terms of the family itself, now 35% of these family units had a related phenotype. Well, that's quite interesting, and it's getting up there. Very small sample size again, very specific. But what this is saying is that when you screen very broadly, we used a lot of genes here. We looked at 1,000 genes here. When you screen for 1,000 genes in and babies, and you find unanticipated mutations, that there's about a 35% chance that at the time you find it, somebody in that family is manifesting that feature phenotype. And by the way, all of the family members were undiagnosed. Nobody had a proper diagnosis, nobody. So if you think about it that way, you're gaining a tremendously interesting insight into somebody in the family in 1/3 of cases. That's not usually the way we think about screening, because we've been trained to think about it not as a family unit, but as an individual unit child. I thought that was really interesting. And it speaks to possibly much greater clinical utility than we've been thinking about. Now, many ethicists don't like this framing because they say the child should not be a window into the health of the adults. If the adults want to get themselves sequenced, they should. But it's not very practical because there is no mechanism for adults to routinely get themselves sequenced. So if you happen to have that window open through the child, my position has been you ought to, or I guess if you want to don't want to mix my metaphors too badly, if that door is open because you sequence the child, then you have a right to walk through it. And this theoretical argument became real for us when 3 of the children were seen to have adult onset cancer predisposition. 2 of them had a BRCA2 mutation, 1 of them had an NSH2 mutation for Lynch syndrome. And all 3 of the parents happened to be, by coincidence, mothers who were carriers of these did not know that they were carriers. So we were faced with returning that to those women or not, letting them proceed in ignorance. We chose to return it to the child and return it to the parent after making sure that we had adjusted our protocol and readjusted our consent. Very elaborate and time consuming, but we did it. These parents said, yes, I want to know if there's an adult condition. And all 3 of these women had risk reducing surgery in the 5 to 6 years following this disclosure, all 3 of them. So this is a use case where unveiling a family mutation that was absolutely unknown arguably saved the life of the mother. It's really hard for me to find that morally inappropriate. I won't show you videos today, but I have some really interesting videos that are coming out in a TED Talk on July 16th about mothers who found out information about their child or even themselves. I also want to mention that we have the pride of being the first to do this in apparently healthy children, but we are by no means the only group. There's the several groups in the United States, now the Guardian study in New York State, the Screen Plus study also in New York City and State, the Beginning study in California, and a study in North Carolina that are sort of the main leaders in the United States. And then there are others in the Middle East that are coming online in Europe, in Asia, and in Australia. So in total, there's about 27 groups around the world that are attempting to do this. We've formed a consortium called the International Consortium on Newborn Sequencing. We've had 3 prior meetings in Boston, London, New York City, and now we're going back to London for October 23rd, 24th. You can, registration is open. This is a low-cost, fabulous meeting. It's just been so transformative. It's the one place in the world all these groups come together. And so if this is of interest to you from whatever perspective, clinical, public health, laboratory, you can either come to the meeting in London or you can sign up and attend it entirely virtually. Let's circle back a little bit and talk a little bit about conventional newborn screening. So as most of you know, this is a program It was started in the 1960s with a heel stick, putting a drop of blood on a piece of filter paper and testing that initially for PKU, phenylketonuria. Because if you didn't adjust the diet of these children very quickly after birth, they went on to have irreversible brain damage and intellectual disability. And so PKU was the defining condition that put newborn screening into motion. It rolled out first for that, then subsequently for additional conditions, and then for a panel of conditions in all 50 states over the next few years. Until very recently, there was a committee called the Secretary's Advisory Committee for Heritable Conditions, which created a recommended uniform screening panel that each state was encouraged to implement, often at its own pace with its own resources. So sometimes it would take years, but it served as a convening body for evidence. And the number of conditions in that, I believe, is up to about 35 or 36. Although states are also able to add on conditions. And some states, like New York State and California, have added on quite a few more. I think the most that any state has added on is a total of 75 conditions. So I say that committee used to be there because in the deconstruction of our federal healthcare system and regulatory system, that committee was just dissolved. So the states are on their own right now as far as how to proceed forward in adding things. But since we started publishing in BabySeq, and especially since these groups have sprung up all over the world, obviously the state public health newborn screening ecosystem in every state has been fascinated by the possibility of adding genes. Now, adding a single gene isn't that big a deal. Actually, every single state has now added spinal muscular atrophy, a genetic test for spinal muscular atrophy, a single gene, because there's a treatment and because those advocacy groups and pharmaceutical groups pushed successfully to get that added. But adding a larger panel, especially if you do it with whole exome or whole genome sequencing, opens up a big can of worms that fundamentally changes the value proposition, fundamentally opens up other possibilities for returning to the genome or exome. We'll just say genome from now on, but it could be an exome as well. And fundamentally changes the risk profile that most people experience and integrate when they're thinking about their child being screening. Let's see how it's done now. So it's done basically now under an unconsented model. And why is it unconsented? Because the states have predominantly decided that this is of such importance that they are not even going to give the parents a choice. This is a legal principle called parens patriae, and it means we, the state, says this is so important, we're going to override the parent's choice. And so very often the way this happens in every birthing hospital is the baby's whisked away. There may or may not be an informational pamphlet. There may or may not be a pilot with something the parents sign. So there might be a little form of consent. But it's not really presented as a choice you can or should turn down. And that's reflected in the sense that 98% of live births in the United States get this done. It's unheard of in anything that's truly offering somebody a choice. I mean, just to be stubborn or contrarian, most people, there would be, whatever you do, there's more people turning it down than that. So it is either truly or effectively unconsented. And that's been justified and justifiable in most people's minds, but privacy zealots have taken this on as a cause and have really pushed back in a few states. And there's real questions developing for the first time since the 1960s as to whether it should be more consented, or whether that will, there's a wrongness about that, in that the very people who are most likely to turn down a consented opportunity are people who would be least in a position to benefit. They might be under-resourced. They might be minoritized populations that distrust the medical system. They might confuse what's being done with, with tracking for law enforcement. So the newborn screening ecosystem has just kind of stayed with their heads low, below the surface, keeping it real, but keeping it on the down low until forced to kind of move this up into the public limelight, because they don't want people to be so aware that they start objecting. There's no enforcement mechanism, if a parent objects in the hospital, really objects, you can't bring in a state trooper to make them do it very easily. It's hard to enforce. So that's the system. But now the system is really interested, and a few states, again, New York State and North Carolina, and now some Florida states have really been actively pursuing ways to do this. There's a recent NIH call for a grant proposal to try to assess the feasibility of how you might roll this out in a subset of states, 5 to 10 states, which we and several other groups are competing for. Those grants just went in this morning. So I'm speaking to you from a slightly dazed post-grant moment. Anyway, so if it's not going to happen or happen quickly as an adjunct to state-based newborn screening, why wouldn't it? Well, it wouldn't, because most people don't think you should add comprehensive sequencing without consent. So now you're talking about layering a consented process onto an essentially unconsented process, which gives people pause. It's going to draw more attention to the unconsented process. Is it going to alienate people when they say, oh, this same public health program that were the good guys for finding the PKU cases, now it looks like, they want to track our genomes. It also just gives these state labs and programs pause because of bandwidth and because of resources, because these guys are state funded. They're often struggling. They're very dedicated. They struggle to get the results back that they're doing. The idea of taking on another couple hundred conditions can feel pretty overwhelming. So that's quite interesting too. How would you even do it logistically? A lot of people confuse what's going on with direct-to-consumer genetic testing if you were to go outside the newborn screening public health system. So you could envision scraping the baby's cheek or taking a droplet of blood, let's say in the first pediatrician's visit. Now that starts to approach population screening. And whenever I get to this point in a talk, I have to remind people, probably not you guys, but I have to remind other people that we're not talking about consumer-facing direct-to-consumer genetic testing. And one of the reasons we're not talking about it is that most of that has been, let's see if this animation works, most of that has been genotyping, like on the left, where you're looking at a single portrait, a single SNP among SNPs, many different SNPs, whereas what we're talking about is sequencing every letter of the genome here, as on the right. And the price point for that has been above most of the direct-to-consumer genetic testing. Also, when we open the door to newborn genome sequencing, we're opening the door to more than just a static moment in time, because we are now opening the possibility of revisiting that genome, right? The genome itself isn't changing over time, but as the child grows, you might find or not find something initially that's problematic. And then as that child gets older, science will have revealed or treatment will have been developed for a new condition. And it becomes salient to find a new mutation. So isn't that an interesting way of thinking about it, as a lifelong genomic resource? And whatever they are or are not, or try or do not try, the state public health newborn screening ecosystem is not set up for this. This has to come out of the care, pediatric care of a child as he or she are growing, as they are growing older. So If you really want to take full advantage of a genome in a young child, you've got to think, well, how can I revisit it? So the public benefit startup company that I co-founded, Nurture Genomics, is trying to do this overtly. It's working through practices, healthcare systems, may eventually work through employers to offer children a way to get sequenced and a navigator system that would allow those families and those pediatricians to revisit, reanalyze, and reassess the genome over time. And that's the one I mentioned at the beginning. If you have a child and you'd like to get on the wait list for that, go to the website, nurturegenomics.com. It's not active yet, but you can sign up. It's going to allow a cheek swab, personalized navigation. And then I'll just end with a reminder of our websites, our social media handles, my email if you'd like to write. And so at this point, with a little more than 15 or 16 minutes to go, why don't I stop sharing as long as you've gotten a chance to look at that. And then would love to engage in questions, of course, but even more, I'd love to hear your thoughts on this, and we could get a conversation going. Thank you very much. I'll stop sharing now.
All right, wonderful. Thank you very much, Dr. Green, for your very informative presentation. As you mentioned, we will now go ahead and start the Q&A portion of the webinar. So if you happen to have a question that you would like to ask, please do so now. Just submit a question in the Ask a Question box located at the bottom of your screen. Okay, let's go ahead and get started here. The first question that we have here says, what are the arguments for and against population-based genetic screening?
Yeah, I touched on this a little bit with the analogy to whole genome, to whole body imaging. The arguments for, of course, are that clearly we're missing, unquestionably, we're missing awareness of genetic conditions. Either in children or adults, there are things we could determine in advance. If you really wanted to just pick a few, you could pick in adults, you could pick the CDC tier 1 conditions, which are breast and ovarian cancer, Lynch syndrome for colorectal cancer, and familial hypercholesterolemia. If you just look for 10 genes that constitute a risk of those 3 conditions, you find that about 1% of the population are carrying them, and almost nobody knows that they're carrying them. So, pardon me. So, thank you. The argument for is very simple. We want to find these things. We want to save people's lives. The arguments against are, well, we could do a lot of things to save people's lives, but our resources are not endless. Is it cost effective? That's a particularly important argument and has been approached from a modeling point of view by David Veenstra and his group in a series of articles that are beautiful articles where they model out the cost effectiveness of these conditions. And I believe that they modeled out, I think it was $65,000 per QALY, which is considered an appropriate amount. Let me just double check that here while we're talking. Is considered an appropriate amount. $68,600 per QALY. So that's not terrible. Most of the time under 70,000, you consider a fairly worthwhile endeavor. So the UK has just moved into policy something which is going to screen all self-identified Jewish families just for BRCA1 and BRCA2. To my knowledge, maybe outside of Israel, that's the only integrated screening program for population genomics that's ever been put into place on a nationwide basis. Other negatives of it, besides cost and effectiveness, are people's fears of privacy invasion, of course, use by inappropriate use by law enforcement, and all the psychosocial wrapper that comes with someone knowing your genomic information. I'll pause there, but feel free to ask for a deeper dive.
Sounds great. Thank you. Okay, it looks like we have a few more here. This next one says, what is the difference between indication-based genetic testing and predictive genetic testing?
So on the surface, this is a simple question. If somebody's sick, you're doing that's indication-based testing. You got a kid with a mysterious syndrome, seizures, big head, dysmorphic features, whatever. You don't quite know what it is. You're going to do genomic testing, either targeted genetic testing because you think you know, or broader genetic testing because you're not sure you know. That's indication-based. In a person who presents as healthy, that's screening, or you could call it predictive or proactive. However, your question unveils a deeper issue, which is really interesting, something I've called quasi-indication based. There's pretty clear lines for what justifies genetic testing, and a parent's instinct is not among them. But when a parent feels like a kid's gotten a little clumsy or has fallen behind in school, that doesn't usually trigger genetic testing. If genetic testing was free and cheap and easily available, easily interpreted, you'd probably not only get people in the indication-based category, but you'd get it in this quasi-indication-based category. Of course, if it was free and easy enough, you could do the whole population, or at least those who want it. So I think of it as a kind of a barbell curve. You've got a large number of testing that goes on that you could consider indication-based. Theoretically, you've got a even larger number that could be screened. But you've also got this sort of amorphous bridge where either the family thinks there's something wrong or the pediatrician thinks there's something wrong, but they're not entirely sure. Again, a way to think of that would be screening again, but it would be screening of a population in whom there's now a slightly higher prior probability because somebody's noticed something's wrong. You can think of screening, broad population, or you can think of screening a subpopulation.
All right, fantastic. Thank you. It looks like we have a question here in the live chat. It says, how do we balance the weight and very real costs of false positives versus the prevalence of true positives with clinically actionable outcomes?
Yeah, great question. The short answer is we don't know enough to do that. Until we have sequenced hundreds of thousands of kids and followed them for years, we actually don't know what the penetrance is. We don't know what the cost effectiveness is really. We're guessing in the dark. We feel some urgency to try to do this anyway because of the conditions that we know we can help. So balancing it is a bit of a leap of faith at the moment. But I would also want us to be very careful with our language. You notice I never, in my whole talk, I never use false positive and false negative, because, especially false positive, because identifying, let's say, a cardiomyopathy mutation in a child, and then you do an echocardiogram and their heart thickness is normal, sounds like a false positive. Hey, I found this mutation, their heart thickness is normal. But I would say it's not. It's only false in that sliver of time. If you follow that child for 5 years, 10 years, 50 years, 60 years, I believe that risk is still there that that child's heart will thicken, heart muscle will thicken. So what you're really identifying is not a false positive, but a risk stratification. And that's different. It's subtly different. False positive suggests to you and to the world, we shouldn't be doing this. We're identifying we're worrying families, we're mobilizing medical resources, all for naught. We shouldn't be doing it. Risk stratification is a more sober strategy that says, I'm going to put people into a risk stratified place where I might or might not do additional surveillance and testing, but at the very least, as a pediatrician, for example, I can be aware that they're in this category. That simple awareness probably fundamentally changes the threshold of action for a pediatrician to act more quickly when somebody has a staring spell. If you knew that a child had a predisposition to epilepsy, even if they'd never had a seizure, and mom comes into you and says, baby's having staring spells, you will fundamentally interpret that differently. If you knew that there's a muscle disease possibility and parent comes in and says child is having trouble walking up the stairs that they never had, you might have called it, this is a real life thing. There's been families whose pediatrician said it was just oppositional behavior. It wasn't. It was a genetic muscle disease declaring itself. And if the pediatrician knows, they can go much more quickly to the category of disease and consider it. So for all those reasons, I talk about risk stratification. I actually try to avoid the term false positive. A false negative is a different issue altogether. I don't know what you mean in a healthy baby. I don't know what you mean by a false negative. I mean, you could mean that baby's going to go on to get cardiomyopathy, and we didn't identify one of the cardiomyopathy genes. That's true. That's fine. Our sensitivity is not perfect at all in genetic testing. There's going to be lots and lots and lots of pathology that doesn't have a monogenic disease risk identifiable.
Perfect.
Yep.
Thank you so much. It looks like we have time for one more here. We had a comment and a question come into the Q&A. It says, Dr. Green, thank you for the insightful presentation. Do you think multiomics has a role in newborn testing?
Yes, I really do. And thank you for asking that. So first, let me just say I'm focused on genomics. I know relatively much less about all the different multiomics. But it's clear, because research is going on in Genomics England and elsewhere, that if you take proteomic profiles, for example, they have their own independent predictive ability of illness, and they're much more dynamic than your DNA, which of course was pretty much the same since birth. Expanding that, you can take transcriptomics or epigenetics. We know that there are regulators that influence the expression of different genes. So that will factor into whether or not you get a particular pathology that you're at risk for. There will be microbiomes, lots and lots of very solid research, but even more speculation about how the gut microbiome influences our health. So absolutely, we're going to have wave upon wave of technological advances. And by the way, we haven't even mentioned wearables, the smart diapers, the chemistry of the urine, the wearables that look at your exercise, your breathing, your sleep, your blood glucose. I mean, there's so much data coming in that's going to be able to be parsed and integrated into predictive models. So yes, there's going to be lots more. I do think about genomics as a kind of tip of the spear, though. And the way we think about it, the way we integrate it, the way we try to move toward proactive medicine in genomics may be a template for how we move in all these other waves of technological advance. Thanks. That was a great question. All right.
All right. Perfect. Well, we will go ahead and close out with that being our final question. Thank you again, Dr. Green, for your time today and for your very important research. Before we go, I would like to thank the audience for joining us today and for their very interesting questions. Questions that we did not have time for today and those submitted during the on-demand period will be addressed by the speaker via the contact information you provided at the time of registration. As a reminder, this webcast can be viewed on demand for 1 year until May 14th, 2026. LabRoots will alert you via email when it's available for replay. We encourage you to share that email with your colleagues who may have missed today's live event. Until next time, everybody, goodbye.